Hey, welcome. Today, we're diving into the journey of something that's literally all around us, but a lot of the time, totally invisible. We're talking about waves. It's this incredible story about energy, vibration, and how pretty much everything from light to sound gets from point A to point B. So, let's get into it.
So to kick things off, let me ask you a question. What in the world connects the bone-rattling sound of a rock concert, a ground-shaking earthquake, and a bat, just doing its thing, hunting in the pitch dark? They seem completely unrelated, right? Well, the surprising answer is waves. To really get that connection, we have to start at the very beginning. Where do waves even come from? What is it that makes a wave, well, a wave?
At its core, a wave is actually beautiful in its simplicity. It all starts with a single little disturbance, a vibration. That vibration then starts to travel, and it carries energy with it. Now, here's the really crucial part. The wave moves the energy, but the stuff it's moving through, whether it's water or air or the ground, that stuff doesn't actually go anywhere. It just passes the energy along.
So you can pretty much describe any wave out there using just 4 key traits. First up is amplitude. That's the wave's height. You can think of it as its intensity or its loudness. Then you've got wavelength, which is just the distance from one peak of the wave to the very next one. Frequency tells us how many of those peaks pass by a certain spot every second. And finally, velocity is, you guessed it, how fast the wave is traveling. These 4 things together give every single wave its own unique fingerprint.
Okay, so we know what a wave is, but how does it actually get around? Well, it turns out there are 2 main ways a wave makes its journey through the world.
On one side, you have your transverse waves. For these, the vibration goes up and down, while the wave itself moves forward. The classic example is a ripple on a pond, or even better, the wave at a football game. People stand up and sit down, but the wave itself travels all the way around the stadium. On the other side, we have longitudinal waves. This is where the vibration is more of a back-and-forth push, in the same direction that the wave is traveling. The perfect way to picture this is a slinky being pushed and pulled.
And sound. Sound is the perfect real-world example of one of those longitudinal waves. It literally travels as a series of compressions, little squished-up bits of air moving through the atmosphere. And this is exactly how a bat's echolocation works. It's just sending out these little pulses of compressed air to build a map of its world. Pretty cool, right?
So far, we've been talking a lot about movement. But a wave's journey is really defined by what it carries. And what it carries is probably the most fundamental thing in the entire universe: energy.
This right here is the single most important job of a wave. Think of it as an energy delivery service. Whether we're talking about the heat from the sun reaching us as an electromagnetic wave, or the incredible force of a tsunami, it all comes down to moving energy from one place to another.
But here's the thing, that energy isn't limitless. As a wave travels out from where it started, like ripples in a pond, that energy gets spread out over a bigger and bigger area. And what that means is its intensity, or its power, gets weaker the farther away you are from the source.
Let's make this feel real for a second. Let's talk about an earthquake. Imagine you're about 100 kilometers from the epicenter. The intensity of that wave, the amount of pure energy hitting a single square meter every second, is a massive 1 million watts. That is an incredible amount of focused power.
Okay, but now, let's say you move 400 kilometers away. That's 4 times the distance. Because that same amount of energy has had to spread out over a much, much larger area, the intensity you feel is way, way lower. It's the exact same wave, but its punch is faded with distance.
So, a wave's journey isn't always through an open field, right? Eventually, it's going to run into stuff. So what happens when a wave finally meets the world?
When a wave comes up against something, it can basically do one of 3 main things. It can bounce off, which we call reflection. It can bend as it passes into a different material, that's called refraction. Or it can bend around an obstacle, which we know as diffraction.
Reflection is the one we're probably most familiar with. An echo, that's just a sound wave bouncing off a wall and coming back to your ears. And it follows this really simple, elegant rule. The angle that the wave hits the surface is the exact same angle that it bounces off. Simple as that.
Refraction is a little more subtle. It happens anytime a wave crosses from one medium to another, like light going from the air into a glass of water. That change makes the wave actually change its speed, which in turn causes it to bend. You've definitely seen this. It's the reason a straw in a glass of water looks like it's broken right at the surface. And then there's diffraction. This is a wave's really clever ability to bend around corners. Think about it.
If waves only traveled in perfectly straight lines, you'd never be able to hear someone talking in the next room unless you were standing right in the doorway. It's diffraction that lets the sound wave spread out and find its way to your ears.
We've been following a single wave this whole time. But of course, the world is full of waves constantly overlapping. So for the last and maybe most fascinating part of this journey, what happens when they collide?
Well, this whole process is governed by a really powerful idea called the principle of superposition. Now, that sounds super complex and scientific, but it's really just simple addition. When two waves overlap at any given point, you just add their heights together. That's it. That tells you exactly what the new combined wave looks like.
And this simple addition leads to two really dramatic results. If the crests of two waves meet, they add up and create an even bigger crest. That's constructive interference. But if a crest meets a trough, they can completely cancel each other out. That's destructive interference, and it's the brilliant trick behind how your noise-canceling headphones work.
Now here's where it gets amazing. When a wave and its own reflection interfere with each other in just the right way, you can create something called a standing wave. It literally looks like it's just vibrating in place. Picture a jump rope being swung really fast. There are some points that barely move at all, we call those nodes, and other points that swing wildly up and down, the antinodes.
And this is the secret behind all music. A guitar string, a piano string, they are all designed specifically to create standing waves. Those very specific frequencies that create these perfect, stable patterns are called resonant frequencies. The lowest one gives you the main note, the fundamental, and all the others create those rich overtones that we call harmonics. So, from an earthquake to an echo, to the notes coming from a piano, it all comes back to the journey of a wave. The truth is, we are constantly swimming in an entire ocean of these vibrations. Radio waves, light waves, sound waves. Which leaves us with one final thought. Now that you understand their journey, what other phenomena in your world could be explained by this amazing hidden dance?